Several websites offer electrical calculators with functions for conduit fill, box fill, wire sizing, and ampacity calculations accessible for download or use on desktop or laptop computers. Electrical Calculator Pro offers a range of tools for electrical calculations. NEC Calculator focuses on calculations related to the National Electrical Code. Calculator Suite provides a variety of calculators, including those for construction and electrical work. Handyman Connect offers a collection of electrical calculators for various tasks. Additionally, several distributors provide electrical calculators and related tools. Klein Tools offers a selection of electrical tools which may include calculators or software. Ideal Industries provides various electrical products and tools, potentially including calculators. Southwire offers resources and tools for electrical calculations and wire sizing. When performing conduit fill calculations, several factors must be considered to ensure compliance with the National Electrical Code, or NEC. Firstly, determine the type and size of conductors being installed. This information is necessary to determine the cross-sectional area of each conductor. Secondly, identify the type of conduit being used, such as rigid metal conduit, electrical metallic tubing, or flexible metal conduit. Each conduit type has a specific inside diameter that affects the allowable fill percentage. Thirdly, consult NEC Table 1 in Chapter 9 for conduit fill limitations. This table specifies the maximum percentage of the conduit's cross-sectional area that can be occupied by conductors based on the number of conductors in the conduit. The allowable fill percentage varies depending on whether the conduit contains one conductor, two conductors, or more than two conductors. For one conductor, the maximum fill is 53%. For two conductors, the maximum fill is 31%. For more than two conductors, the maximum fill is 40%. Fourthly, calculate the total cross-sectional area of all conductors to be installed in the conduit. This can be done by referring to NEC Chapter 9, Table 5, which lists the cross-sectional area of various conductor sizes and types. Fifthly, determine the inside area of the conduit. This information can be found in NEC Chapter 9, Table 4 for various conduit sizes and types. Sixthly, calculate the allowable fill area of the conduit by multiplying the inside area of the conduit by the allowable fill percentage from NEC Table 1. Seventhly, compare the total cross-sectional area of the conductors to the allowable fill area of the conduit. The total conductor area must not exceed the allowable fill area to comply with the NEC. If the total conductor area exceeds the allowable fill area, increase the conduit size or reduce the number of conductors in the conduit. When performing box fill calculations, several factors must be considered to ensure compliance with the National Electrical Code. Firstly, determine the size and type of conductors entering the box. This information is necessary to determine the volume allowance for each conductor. Secondly, count the number of conductors in the box. This includes all conductors that originate, terminate, or pass through the box, with some exceptions as outlined in the NEC. Thirdly, determine the volume allowance for each conductor based on its size. Refer to NEC Table 314.16b for conductor volume allowances. For example, a number 14 AWG conductor has a volume allowance of 2.0 cubic inches, while a number 12 AWG conductor has a volume allowance of 2.25 cubic inches. Fourthly, count the number of device yokes or straps in the box. A device yoke or strap is the mounting hardware for devices such as switches and receptacles. Each device yoke or strap counts as one conductor based on the largest conductor connected to the device. Fifthly, count the number of equipment grounding conductors in the box. All equipment grounding conductors entering the box count as one conductor based on the largest equipment grounding conductor entering the box. Sixthly, count the number of conductor terminations, such as wire connectors or splices, in the box. All conductor terminations count as one conductor based on the largest conductor connected to the terminations. Seventhly, calculate the total volume required in the box by summing the volume allowances for all conductors, device yokes or straps, equipment grounding conductors, and conductor terminations. Eighthly, determine the minimum box volume required based on the number of conductors and devices in the box. Refer to NEC Table 314.16 for minimum box volume requirements. Ninthly, compare the total volume required in the box to the minimum box volume required. The total volume required must not exceed the minimum box volume required to comply with the NEC. If the total volume required exceeds the minimum box volume required, increase the box size or reduce the number of conductors or devices in the box. When performing wire sizing calculations, several factors must be considered to ensure compliance with the National Electrical Code. Firstly, determine the load current that the conductor will carry. This is the amount of current that the circuit is expected to draw under normal operating conditions. Secondly, determine the ambient temperature in the area where the conductor will be installed. The ambient temperature affects the ampacity of the conductor, as high temperatures reduce the conductor's ability to dissipate heat. Thirdly, determine the type of insulation on the conductor. Different types of insulation have different temperature ratings, which affect the conductor's ampacity. Fourthly, determine the number of conductors in the raceway or cable. When multiple conductors are installed in close proximity, their ampacity must be derated to account for the increased heat generated by the conductors. Fifthly, consult NEC Table 310.15b16 for the ampacity of conductors based on their size, insulation type, and temperature rating. This table provides the allowable ampacities for conductors under various conditions. Sixthly, apply any necessary derating factors to the ampacity of the conductor. Derating factors are used to reduce the ampacity of the conductor to account for ambient temperature, the number of conductors in the raceway or cable, and other factors. Seventhly, select a conductor size that has an ampacity equal to or greater than the load current after applying any necessary derating factors. The selected conductor size must also be large enough to handle the voltage drop in the circuit. Eighthly, calculate the voltage drop in the circuit to ensure that it does not exceed the allowable limits specified in the NEC. The NEC recommends that the voltage drop in a branch circuit should not exceed 3%, and the voltage drop in a feeder circuit should not exceed 5%. Ninthly, if the voltage drop exceeds the allowable limits, increase the conductor size to reduce the voltage drop. When determining ampacity, consider the definition. Ampacity is the current, in amps, that a conductor can carry continuously under the conditions of use without exceeding its temperature rating. The ampacity of a conductor is affected by several factors, including the conductor's size, insulation type, ambient temperature, and the number of conductors in a raceway or cable. The National Electrical Code provides tables and guidelines for determining the ampacity of conductors under various conditions. The ampacity of a conductor is directly related to its ability to dissipate heat. When a conductor carries current, it generates heat due to the resistance of the conductor. The amount of heat generated is proportional to the square of the current and the resistance of the conductor. If the heat generated exceeds the conductor's ability to dissipate it, the temperature of the conductor will rise. If the temperature of the conductor exceeds its insulation rating, the insulation can break down, leading to a short circuit or fire. The ampacity of a conductor is also affected by the ambient temperature. As the ambient temperature increases, the conductor's ability to dissipate heat decreases, which reduces its ampacity. The National Electrical Code provides derating factors for conductors installed in high ambient temperature environments. These derating factors reduce the ampacity of the conductor to account for the increased ambient temperature. The number of conductors in a raceway or cable also affects the ampacity of the conductors. When multiple conductors are installed in close proximity, the heat generated by each conductor can affect the temperature of the other conductors. This reduces the ability of each conductor to dissipate heat, which reduces their ampacity. The National Electrical Code provides derating factors for conductors installed in raceways or cables with multiple conductors. These derating factors reduce the ampacity of the conductors to account for the increased heat generated by the other conductors. Conductor insulation types determine the temperature rating of a conductor. Different insulation types have different temperature ratings, which affect the ampacity of the conductor. The National Electrical Code lists the temperature ratings of various insulation types in Table 310.104a. It is important to select a conductor with an insulation type that is suitable for the operating temperature of the circuit. Selecting the correct wire size is very important. Wire size is determined by its circular mil area. The larger the wire size, the more current it can safely carry. Firstly, calculate the design current. Determine the maximum current the circuit will carry. This is based on the load connected to the circuit. Secondly, determine the allowable ampacity. Consult the NEC to find the allowable ampacity for the wire based on its insulation type and temperature rating. Consider any dating factors for ambient temperature or the number of conductors in a raceway. Thirdly, select the wire size. Choose a wire size with an ampacity equal to or greater than the design current. Account for voltage drop. Check the voltage drop to ensure it is within acceptable limits. The NEC recommends a maximum voltage drop of 3% for branch circuits and 5% for feeders. If the voltage drop is too high, increase the wire size. Size the overcurrent protection. Select an overcurrent protection device, such as a circuit breaker or fuse, with a rating that protects the wire and equipment. The overcurrent protection device should not exceed the wire's ampacity.